All right, thank you very much for coming to our talk. It's good to see you all here. After seeing some novel attacks and some novel vulnerabilities in this couple of last days, I realized that we will probably take you to a journey back to 90s, so I hope you will enjoy our talk. First, a little bit about us. We are Francesco and Stanislav. We are security researchers at Forescout with their labs, and mostly we do vulnerability research, some threat hunting and threat intelligence. And here I would also like to list the names of the people who helped with this research, and special thanks for ChatGPT for generating images that will set the tone of this presentation. So first, a little motivation. It's always in the news that the IT infrastructure is targeted by the attackers. However, we noticed that a little attention has been brought to the OT and IoT network perimeter. The question that we ask together with other researchers, whether these kind of devices can be as attractive to the attackers in terms of the returns of investment and the impact. The manufacturers of IoT/OT devices keep relying upon two principles. One is security through obscurity, and the other one is the principle of many eyes, also known as Linus law. The first one is about the fact that they often tend to encrypt their firmware or hide the hard-coded secrets, thinking that nobody will be able to discover them, and you don't need to secure those things. And the latter principle is about the open source components that they integrate as a part of their firmware or software packages. And it's a common belief that if many other people are looking in those reporting vulnerabilities, all the manufacturers have to do is to follow the disclosures and just update regularly. And if there are no vulnerabilities found by other people, there's practically nothing to do. So we actually hypothesized that these two principles don't benefit manufacturers at all. In fact, only the attackers benefit upon them on a large scale. And just to explore several of these points, we looked at the popular family of the edge IoT and OT devices, which are Sierra Wireless Airlink gateways. So here is a brief outline of the talk. I will first talk a little bit about the vulnerability target, the vulnerability research target that we have selected. And then Francesco will guide you through the steps that we did to find some of the vulnerabilities in there, and he will show them. Then I will take over and show you how simple it is to root one of these devices and what could be the potential impact of the findings that we have uncovered. And finally, we will offer some takeaways for both researchers and manufacturers, which hopefully could be useful. So why have we decided to look at these devices in particular? We were looking for an impactful edge networking device, and Sierra Wireless has a series of Airlink devices, which are gateways, and they are quite popular brand, along with devices from some other manufacturers, such as Teltonika, Moxa, and others. We also found that quite a number of these devices can be found online through Shodan or other search engines, so probably attackers could be looking at those as well. And the industries where they're used are quite different. So they're used for electrical substations, for vehicle transportations. We found on the website they advertise that these are used in police vehicles. They can also be used in healthcare facilities, oil and gas fields, and other places. So it seems to be part of the critical infrastructure somehow. But most importantly, these devices are often used together with cellular connectivity, and they are working in the areas where the traditional network connectivity is limited or not available. Here's just a small example from the website of Axis, who are manufacturers of IP cameras, and here they show how their devices can be combined together with one of the Airlink devices from Sierra to provide video surveillance in areas where the traditional networks are not available. So then we looked a little bit at Shodan, and we took one of the components that runs on these devices. It's called AC Manager, and it's like a web UI that is used to configure and manage these devices. And naturally, it has various fingerprints that we tried, and we already have found about 86,000 devices on Shodan. So the vendor says specifically that this web UI should not be exposed to the wide networks, but still we find quite a lot of them are exposed. And yeah, it seems to be that these are quite popular. Finally, before fully committing to this research, we had a look at the state of the art and what other people did, and we found quite a few reports in the several past years. In total, there were 36 vulnerabilities, and what we immediately noticed is that the researchers have been focused mostly on the internal and proprietary components, and nobody has actually looked at the open source that runs along in this firmware. So we decided that we start with the internal components, the most popular ones that have been already researched, to see if we can find something interesting there. And then we focus on the third-party stuff to see if some things have been overlooked. And now Francesco will guide you through the journey that we had.
Thanks, Stanislav. So to perform our research, we adopted the following methodology. We obtained devices and firmware, we decrypted the firmware, we performed a black box functional analysis, we identified and prioritized all the components, and we performed a static and dynamic analysis of the selected components. We will see all these steps in the next slides. So we decided to focus on devices that ship with Helios or Airlink enterprise operating systems, which is running an embedded Linux system. And in the past, parts of Helios have been were researched, but without a focus on the third-party components. We also could not find any software bill of materials, and this was an additional selection criteria. We picked an Airlink LX60 because of its versatility, availability, and its low cost, and we downloaded its firmware from the Sierra Wireless website. These devices are mainly used for primary or backup network connectivity for retail, POS, taxis and transport fleets, small businesses, industrial IoT, and for building automation. We have noticed that the firmware package for some end-of-life devices is unencrypted, and many internal binaries contain debugging symbols. This was really helpful in understanding some parts of the Helios system. Unfortunately, the latest Helios firmware is encrypted. However, we found that Ruben Santamarta from AO Active Labs was able to decrypt it a few years ago. The new firmware is still using the same encryption technique, which is based on AES in counter mode, and the encryption key is derived from the firmware version plus a custom seed value. We used Docker to emulate this AC manager, which is a web application to manage the router and its configuration. And we also emulate its dependencies, and we run it through QEMU ARM system emulator. This was really handy to emulate parts of the system, and especially for debugging, because the device had no debugging capabilities. Helios is large, it includes many different components, so we had to prioritize the analysis in order to maximize the return of investments from an attacker's perspective. So among these components, we analyzed, first of all, this AC manager, which has been found vulnerable in the past, but it remains commonly exposed to the internet. We also analyzed this AT command interface, which also looked promising because it could be exposed through Telnet. We didn't find any software bill of materials, but there are many open source components integrated into the system, but apparently no one has looked at how these open source components are actually integrated into Helios. Indeed, we found a vulnerability in TinyXML. You can see in the table a list of the main open source components, and we decided to focus on RP, PPPoE, OpenNDS, TinyXML, and libmicro-HTTPD, which is a dependency of OpenNDS. Now we will show you the vulnerabilities we found in the old code. This is a brief overview. In total, we found 21 vulnerabilities in Helios and in its open source components. 15 are in the open source components, and 10 affect Helios directly. We found hard-coded credentials, multiple denial of service issues, a couple of store cross-site scripting vulnerabilities. We found multiple command injection and remote command execution issues. The first vulnerability we found was in TinyXML, which is a small project for parsing XML document. It has been replaced by TinyXML2 a few years ago, but we found that the AC manager is still using the old and unsupported version. It mainly uses it for the authentication procedure. We searched for existing vulnerabilities that affecting the TinyXML, and we found one. So we decided to implement a simple fuzzer for TinyXML through libfuzzer, and we found a new vulnerability in a few seconds. The first and existing vulnerability that affects TinyXML and AC Manager is an infinite loop condition that was never fixed. And to trigger this condition, we have to send, through a POST request, a sequence of malformed bytes, where the first 3 bytes are ensuring that the document is interpreted as encoded in UTF-8. In this case, it will enter inside the case branch at line 10, and then to enter the second branch, we have to send another EF bytes. And then to trigger this infinite loop condition, we have, and basically to enter the missing S branch, we have to send a null byte in P+1 or P+2. In this case, the P pointer will be never incremented, and this leads to an infinite loop condition and a denial of service. The second vulnerability we found we found this vulnerability through the fuzzing, and basically in this case it's possible to reach a debugging assertion again by sending a sequence of malformed bytes. In this case, the AC manager will crash, and then it will restart in a few seconds, but we can keep this infinite loop condition, this denial of service, by sending the sequence of bytes in a loop. We found several other vulnerabilities in Helios in this AC Manager application. We found a null pointer reference in the login procedure, a couple of store cross-site scripting, and hard-coded TLS private key and certificate, and hard-coded root password hashes. The first cross-site scripting allows an attacker to replace legitimate HTML pages by uploading an arbitrary file with arbitrary content, such HTML and scripts, through a poorly checked file upload form. The AC Manager allows users to upload a configuration template for the device in XML format. And in this case, you can see from the picture that we uploaded our malicious file with arbitrary tags after the XML tag, and we could also specify an arbitrary name and extension. So all these files are uploaded inside the directory var temp AC Manager user upload, and this directory has a symbolic link www.user_upload, which is pointing to it. The AC Manager maps the URI /admin/ to these symbolic links to allow users to download the uploaded configuration templates. And it maps also to the www.autoviewer directory, where all the HTML pages and the index of the AC Manager are located. So basically, an attacker can upload a file with an extension. We try to upload a CGI script, but it's not longer executable after a fix for a previous similar vulnerability. And the content validation is really poor. Indeed, the AC Manager just checks for the presence of the XML tag. And basically, if we upload file with existing file names, such as the index page, they will be served instead of the original ones. So if we upload the file AC Manager x.html, this will be served instead of the original one, because the upload folder has a precedence. And we can see the consequence here. We uploaded our index page with our arbitrary and malicious scripts, and basically this page will be shown, but this will be shown just to authenticate the users. So we, after a closer inspection, we found the faulty REST key and certificate, which is meant to be replaced by users, but actually we discovered that 22,000 devices are using this default certificate, and this may be exploited through a man-in-the-middle attack, and credentials can be stolen. The AC Manager allows to enable a diagnostic shell through the user interface, and this starts an SSH server. This diagnostic shell allows the Sierra Wireless Tech support to access the router through a root shell. And the root shell is, the access to the root shell is allowed just to the Sierra Wireless Tech support. By default, the root login is disabled, and when this option is enabled, a hard-coded hash for this root user is added to the etc shadow file. We discovered that the hash is hard-coded into the command X binary and is very poorly obfuscated through a substitution cipher. We also discovered that this hash is the same for different devices of the same vendor. Unfortunately, the password have a decent entropy, so we were not able to crack it, and we had to find another way to root the device. We also found several issues with the captive portals. The AC Manager allows to enable a captive portal on the Wi-Fi interface. A captive portal is a web page accessed with a web browser that is displayed to newly connected users of our Wi-Fi networks before they are granted access to the rest of the network. And the AC Manager provides a simple captive portal based on OpenNDS and an authenticated one based on Kuvachili. OpenNDS is an open source captive portal forked from Nodog Splash. It's a mature project, but we were not able to find any public CVEs, and this is basically triggered our curiosity. Indeed, we immediately spotted that Helios used the version 9.1.1, while at the time there was the 9.10. So we decided to look at the repository, and we found a patch with a commit for a potential null pointer segmentation fault. So we looked at the patch diff, and we understood the root cause of this issue. There was a missing check on the presence of the HTTP header, accept header, and basically the pointer at line 18, there wasn't this check, so basically this pointer pointed to a null if that header was missing, and then this pointer was used inside the string compare function, and this caused a segmentation fault. Actually, this issue does not affect any OpenNDS release, but we found a similar code and decided to do some variant hunting. And this is what we found. In this case, again, there is a function that is initializing the user agent pointer to null. So this, again, is a pointer to the HTTP header user agent. And this pointer is not checked, and it's used inside the functions at line 22 and 23. And basically, if the header is missing, this pointer will remain to null, and then it's used inside the string length function, and this triggers segmentation fault. We found 5 more issues exactly that exhibit this anti-pattern, this same anti-pattern. By design, OpenNDS relies on the ability to execute external bash scripts for different purposes. And in this case, this execute ret function executes these scripts under the hood through the function popen from libc, and the command is passed as a string. We found several issues with this design. For example, if the unescape callback is enabled in the OpenNDS config, an attacker can execute arbitrary commands by crafting HTTP requests. We found 4 more issues like this one. Actually, none of them affect Helios because Helios uses the default configuration of OpenNDS, but we may find this issue in different products and services where an attacker can modify the configuration file either directly or indirectly. And you can see here a screenshot of a malicious crafted HTTP request. Now, let Stanislav explain you how we managed to root the device.
Thank you.
Thanks.
All right, so that hard-coded password hash, we could not easily crack it, but we really wanted to get the root. So we started looking around. And while looking at OpenNDS, we found a classical buffer overflow vulnerability. You may find a lot of those as examples in the book called 24 Sins of Software Security. It's quite interesting. And the vulnerability itself is pretty simple. It can be triggered by sending just a GET request to the captive portal, specifying a very long query string. And in this case, it has to be more than 8 kilobytes. So if we manage to exploit this, it's actually pretty good because by design, OpenNDS runs as root because under the hood, it has to, for example, use IP tables to do network segmentation and all the other things. So the vulnerable functionality is in the get query function. I will not show you this because it's too long, but it's very trivial. So this is very good, looks promising, but to actually understand whether it could be exploited on the device that we had at hand, we had to do some extra work. So we had this LX60 Airlink router from which we were able to download the firmware. And we started by looking at the OpenNDS binary that was available there. Immediately we saw it was a 32-bit ARM executable. It has all the full symbols, which was very nice. It was not a positional independent executable, which means we could easily jump to all the virtual addresses of the functions within the binary. And the Alios package itself contains lots of useful binaries that we can use for leaving off the lens attacks, which can simplify things a lot for us. Unfortunately, the non-execute bit was enabled during the compilation, so there was no use of injecting the shellcode into the stack or the heap, so we had to find other way. And the get query function was so buggy, not only it had the buffer overflow, it didn't actually properly copy the query string to begin with, so we were severely limited in our write capabilities, unfortunately. Just to summarize, we had only 36 bytes that we could keep on the stack just before we reached the return address, and we couldn't write anything past the return address because it would contain zeros, and the overflow will stop when it sees the first 0 byte because they are using the string copy function to do that. And finally, the ASLR was enabled, but we know that on 32-bit systems, there may be some limitations to that. Still, to defeat it, we needed to find a way to leak some memory to make sure that we can do something useful. And having all these constraints in mind, we started looking inside the binary. And while playing with AC Manager, we found a window that shows all the syslog and debug messages from different daemons and services that run on the device. And OpenNDS is one of them. And for example, it has this debug function that prints various debug messages. And it has a parameter that is called level, which corresponds to the debug level. And if the value of this parameter is unsupported, it will print a corresponding message along with the invalid value provided. And so if we use the stack overflow that I just showed you to directly jump to this function immediately after the vulnerable code exits, it will print an address. And that address happens to be in the thread local heap where all the other variables related to the GET request are located. And they're located at the fixed offset from this variable. Furthermore, the limitations of ASLR because of the page alignment essentially set only 2 starting base addresses which this thread local heap can have. So basically, it's one of these 2. And we also know that all the other variables that we may be interested in, they are located at the fixed offset. So this looks good. And this is basically how we manage to exploit the device. So while playing with this a bit more, we realized that when we just send a GET request, we can put anything into the URL, and it will not be sanitized, truncated, or encoded. So we can store any data that we like. And at the same time, if you look to the left a little bit at the disassembly, we see that when the vulnerable code exits, it does the traditional routine. It pops some values into the register starting from R4 through R11 and program counter. And this is actually the data that we control through the overflow. So essentially, we can set anything into these registers over there. And finally, we can override the program counter with an address of the function where we wish to jump. We also looked at the binary. We found a very neat gadget that involves the execute red function that Francesco has already shown you. Basically, execute any shell command internally. And the gadget is at the bottom of the screen, and basically what it does, it takes whatever we have in the register R4, places it into the register R2, which will be actually the command parameter of the command that will be executed as root. And then it will proceed with executing that function. So basically, all we need to do to achieve OS command execution as root, we need to place the command that we wish to execute into the URL, and then we need to overflow the query string in such a way that we put an address of that URL into the register R4 and the address of the gadget where we eventually wish to jump into the program counter. So when the vulnerable function exits, we jump to the execute red function initialized with the command that we wish to execute. And with the example of the command you see on the upper right, we could easily get a reverse shell on the device using the BusyBox binary that ships with the device. And from there, we could change the root password, start an SSH service on all the network interfaces, and essentially do with the device everything that we want. Right. Now I would like to discuss potential impact of these devices and vulnerabilities in these devices in particular. As we have already discussed, we found about 80,000 of different devices through Shodan that should not be exposed, but they still are, so they present risks. We also try to see examples of different organizations that expose them for some reasons, and we found some examples of organizations from power distribution networks, national health systems. There was some waste management, retail, and vehicle tracking. So all these areas where these devices could be potentially used. As for the open source components in which we found vulnerabilities, we also tried to see what other products or companies are relying upon it, and we find its traces in products of about 29 vendors. Unfortunately, the impact here is really hard to assess because we don't really know the context in which it is used and whether this functionality is exposed to the potential attackers. The only thing we can say here is that, unfortunately, these vulnerabilities in TinyXML will never be fixed because the project is already decommissioned. And these vendors, if they find themselves vulnerable and affected, they will have to deal with it themselves. For OpenNDS and Nodox Splash, the vulnerabilities have been already disclosed and fixed. But for OpenNDS, the vulnerabilities were only fixed in the newest, latest branch, which is version 10. The version 9 that is still in use remains vulnerable, unfortunately. We could not find many products that are relying upon this, or at least list them in their software bill of materials, but we know for sure they are used in the popular Linux systems for routers, OpenWRT, and DDWRT. Right, we also found that, that there exists an additional way to configure the device through the Telnet protocol. It's called the AT command interface. We also did a little bit of research on that, but we didn't find anything. But most interestingly, it actually allows you to fingerprint the model of the device when you connect to it. And so out of those exposed devices in Shodan, we tried to also fingerprint those using this particular command interface. And these are the numbers that we tried that we could achieve. And as you can see from the table on the left, most of these devices are actually already end of life, which means they for sure will not receive the updates for the vulnerabilities that we have found. And most likely they did not receive vulnerabilities for some of the previous disclosures. We also tried to fingerprint the version of Alios that these devices runs, and we saw that more than half of them actually running very old version which did not receive security patches even for some of the previous disclosures. So this is a bit worrying. Having all that in mind, we're also interested to see if the attackers may be targeting these devices specifically, because we know if you have a device with an open port, everybody will try to do something to that. So to that extent, we took the AC manager binary we extracted from the Alios package, and we created some custom honeypots, which we exposed to different geographical regions. And then we just exposed it, and the experiment lasted for about 2 months. In this time period, we observed more than 5,000 IP addresses trying to do something with these devices, but mostly there were just indiscriminate attacks and some ways to collect information. We've seen a lot of port scans, some attempts to disclosure information or to fingerprint, There is a gazillion of PHP or Java-based web application framework attacks. We still see a lot of Log4j, for example, for whatever reason. We saw some attempts to fingerprint and exploit several OT and IoT-based devices. One of them is Siemens SL7, as always. Then there are Sonic Wall firewalls, Netgear devices, etc., etc. And most of the attacks, as the end goal, wanted to deploy some kind of malware onto the device, which in most cases was some kind of a Mirai variant. But finally, looking through the data, we managed to find the needle in the haystack, and we observed several IP addresses attacking the honeypots with Airlink-specific vulnerabilities periodically. So these vulnerabilities actually were published back in 2019 by Cisco Talos as one of their disclosure to Sierra Wireless, and they made a blog post where they released proof of concept for some of them. These vulnerabilities require for the user to be logged in, but the attackers here rely on the fact that most of the time the passwords are pretty weak and people just leave the default passwords on the device. So what we've seen they're doing, they're trying to log in successfully using the default password that we left on the device, and then they use some of the information disclosure vulnerabilities to fingerprint the device, see what it actually does, and then they use the OS command execution vulnerability through the unrestricted file upload in order to do something to the device and possibly take it over. So as I said, apologies, as I said, we only saw the exploit attempts for those vulnerabilities for which the proof of concept has been already publicly released. For those which don't have a proof of concept, we didn't see anything. So it's a long shot to make this conclusion, but probably the attackers are just, they find something they can readily use, they just go for it. And this is just an example for that. On the right, you can see the original proof of concept released by Cisco Talos, and on the left is the actual exploitation attempt that we observed. So the only thing that changed is just the user agent and the actual command they wanted to execute, which was to drop some malware sample onto the device. Right, and here, just briefly, I want to sketch a possible attack scenario using these vulnerabilities. For example, back in 2014, there was a hacker group called Dark Hotel, and what they did, they found several issues on routers that are typically present in some luxurious hotels, and they were infiltrating those devices in order to deploy malware to some of the guests they wanted to spy on. So here you can see depicted an example of a temporary healthcare facility that could be, could be present in any place. This could be actually your hotel or a security conference. It doesn't really matter. What matters is there is an edge networking device that has a captive portal to give network connectivity to visitors, users, or personnel. And the attacker can simply use the remote code execution vulnerability that we demonstrated to infiltrate the device, and then they can do exactly the same as these guys did back in 2014, or move laterally or do whatever, because this actually device lies on the intersection of all the networks it manages. So they have very wide capabilities. Sorry. So finally, I would like to give some takeaways and maybe some recommendation. Some of it may sound trivial, but this still happens to be true. So while many people actually look at the new vulnerabilities and they're worried about the new stuff, there's still a lot of significant risk that is posed by the old vulnerabilities, especially in the older software, that seems to be robust, and it doesn't warrant too much attention while it still does. And especially this risk comes from the devices that are not patched in a long time or cannot be easily patched. So we just call attention to this. As we have demonstrated briefly, but this is still a common knowledge, the exploit mitigation on embedded devices are pretty much a nuisance for the attacker. They don't really protect anybody. They just delay the exploit attempts by a little bit, a few milliseconds perhaps. So it's better not to rely on them alone, but make sure that the code is secure in the first place. And we also advise to remove all the unused binaries or the dead code from the device, because These actually represent a significant crawl space for the attacker, as we have used one of the binaries available there, which should not be there. It has no place on that distribution. And of course, the dead code gives you more gadgets and more things to do with your exploits. For the manufacturers, we also advise to provide a thorough root case analysis for the vulnerabilities that researchers report them, because one of the vulnerabilities that Francesca showed you was a consequence of incomplete fix for the previous one reported a few years ago. So when somebody sends a proof of concept, it's better to try to examine the root cause of the vulnerability more thoroughly, rather just to then patch the symptom of that the proof of concept uncovers. Right, and for the researchers, on the other hand, we call for sending a more thorough vulnerability reports with good proof of concept, and it's always better if you do the root cause analysis yourself, because that makes the report much more valuable, and it's much less work for the manufacturers, or especially the maintainers of open source projects, to investigate and to fix. So if you really want to help, make sure you do this always. And finally, yeah, it's always a good idea to be nice to the researchers from the manufacturer standpoint, and we would like to thank Sierra Wireless for being exactly that. They were extremely responsive, and they managed to fix everything on a very short notice. And finally, going back to the points we had at the very beginning of our presentation, just to reiterate, we showed that IoT and OT devices, especially those that exist on the edges of network, pose a significant risk that can be compared with the IT infrastructure. At the same time, they're much easier to exploit. So we advise to avoid security by obscurity and adopt the secure by default approach, because, yeah, if it's a hard-coded password, no matter how you obfuscate it, it's going to be found easily. At the same time, the many eyes principle that everybody keeps relying upon when using open source components is not good anymore, unfortunately, because the maintainers of open source projects are overworked. They don't really have time to fix or find bugs, so they require attention with that, and the vendors cannot simply take a piece of code that somebody else wrote, integrate it into their stuff, and yeah, keep pretending that it's not theirs. So if you integrate something, it's your code now, you have to do security research on that, you have to do security testing, and we also call for support from vendors to the open source project by helping fixing bugs of the projects that they use, by providing technical expertise or any other help that they can provide. So with that, I would like to thank you for your attention, and we have a couple of minutes for the questions. All right, I see that there are no, oh, there's one, I think.
Have you found traces which embedded distributions were used on those devices that you attacked?
Right.
And which ones will be more or less vulnerable?
You mean the Linux distributions,
Yeah.
right? I think they have the custom one. I can only tell you more or less the kernel that they use, but I think they have the homebrew one. So it's not an off-the-shelf distribution.
Yeah.
So probably, yeah, it's actually the distribution was okay. It's more or less the problem with the older binaries and the way they are integrated.
More than the distribution.
Yeah, more than the distribution itself. So it's more the actual components, the software components that run there.
Yeah.
Right. Okay, so if you want to know more later, you can always ask us, find us here, or you, unfortunately, I forgot to put the link to the report, but we have a technical report where we have much more details than we could give in this talk. So yeah, feel free to ask me and I will share the link with you. Thank you very much.
Thank you.